Okay, let's start. So today we're gonna going to chapter 4. So chapter 4 on continuity. So let's start with some exercise. So example 1. Suppose f is a real function defined on R, which satisfies this limit as h goes to 0, f of x plus h minus f of x minus h equals to 0. Does it, for every x, does it imply f is continuous? So looks like it's continuous, right? Because if h is very small, then f of x plus h and f of x minus h, they are close. But in fact, it is not continuous. So no. So here's a counterexample. So f of x is equal to 1 if x is an integer, and is equal to 0 if x is not an integer. So what does f look like? So this is, say, 1, it's here. So 2, it's here. And 3, it's here. So this is the graph of f of x. So let's see. If say if x is an integer, then we claim that this is true for this x. Why? Because we take any h, say any h greater than 0, say this is x is equal to 1, and so here is x plus h. As we can see, f of x plus h is always equal to 0 as long as h is positive. Same thing as x minus h. So f of x plus h minus f of x minus h, since they're both equal to 0, this is equal to 0. Okay, so this is true for all h greater than 0 and less than 1, right? For all h sufficiently small, this is true. So this is always equal to 0, then you put a limit, it's still equal to 0, okay? So if x is not equal to a integer, say x is here, all right? So x is here, so x is some distance away from the integers. So as we can see, x is certain distance away from 3 and certain distance away from 2. Okay, so here it's even more obvious. If h is sufficiently small, that means it's away from these two integers, then f of x minus h and f of x plus h are both 0, right? So their difference is equal to 0, and we take limit is still equal to 0. But as we can see, this function is certainly not continuous, right? Specifically, it's not continuous at the integers. So we just found a counterexample that f satisfies this equality, but f is not continuous. Okay, next problem. If f is a continuous mapping of a metric space X to a metric space Y, show that f of closure of E is inside the closure of f of E. Okay, so proof. Also for every E in X. Okay, so how do we show that? If we want to show this is inclusion, we want to show that every element of this set is inside this set. Okay, so take any x in E closure, we want to show f of x is inside f of E closure. Okay, so how do we do that? So here's the graph. So this is x, this is f, this is y. Okay, so here is a small x. So this is f. Oops, sorry. Okay. So x, and this is f of x. Okay, so we take any neighborhood of this f of x. Okay, let's call this neighborhood O. All right, so f is continuous, right? So we can look at the pre-image of this neighborhood O. Okay, so f inverse. All right. So we know the pre-image of the open set is the open set, right? So that's an open set containing X. So this is F inverse of O. Okay. So since X is in the closure of E, right? So there exists a point U in E such that U is in F inverse of O. Okay, so then what can we say about this point U? So f of U is inside O intersection f of E, right? Okay, so f of U is in O, that's by definition of O, and f of U is inside f of E because U is in E. Okay, so O is any neighborhood of f of x. So O is any neighborhood of f of x, right? So that follows. Then it follows that f of x is in the closure of f of E. Okay. All right. So okay. So next, so we want to give an example that to show this inclusion can be proper. Okay, because intuitively speaking, this looks like it should be equality. But why do we only show the inclusion? Because in some cases, the inclusion can be proper. So here is an example. I'm going to write over here. So f, say it's a continuous map from R to R, and we define f of x to be x over 1 plus x squared, and this is continuous because it's a rational function and the denominator is bounded away from 0. So we can let E to be the closure of E is equal to 1 to infinity, right? In this case, E and its closure are the same. Let's look at what is f of E. So f of E, in this case, as we can see, is 0 to 1 over 2. Because this, for when x is in this set, it's always strictly positive, right? It can never reach 0. So it does not include 0, right? But what is f of E closure? So the closure of this set is from 0 to 1/2. Okay? So here, because E and E closure are the same, you can add the closure there. So as you can see, this is a proper subset of this because this does not include 0, but this one does. Okay, so next one, this one is relatively straightforward. So we let f to be a continuous function that goes from a metric space X to R. Okay, let Z of f denote this the zero set of f. Okay, zero set of f. So what does it mean? It is the set of all p in X such that f of p is equal to 0. Okay, so show that this zero set is closed. Okay, so how do we show that? By definition, the zero set of f is the pre-image of 0 under f, right? So 0, since it's a singleton, it's closed, right? So this 0 set is closed because it only contains one point, right? And by characterization of continuous function, um, if f is continuous, then the pre-image of closed set is closed, right? So it follows that z of f is closed. All right. Okay, next problem. So we have two functions, f and g. They are both continuous from a metric space X to a metric space Y. And we let E to be a dense subset of X and show that f of E is dense in f of X. Okay, so that's part A. Part B, if f of p is equal to g of p for all p in E, then f of p is equal to g of p for all p in X. So what does it mean? So part A is straightforward, right? We want to show the f maps a dense set. So the image of a dense set is dense in the whole image. Okay, and part B says if two continuous functions agrees on a dense set, then they actually agrees everywhere. Okay, this is intuitive because at some point if they do not agree, that means f and g, fp and gp are some distance apart, right? Then we can pick a point that's very close to p, that's in E, but they do agree, so that will violate the continuous assumption. Okay, so how do we prove that? So this part A, let's do part A first. So to show f of E is dense in f of x, we want to show that the closure of f of E is equal to f of x. Okay, or so how do we do that? Well, f of x is equal to f of E closure, right? Because E closure is equal to x. That's the definition of dense set. Okay, so by a previous problem, we showed that f of E closure is inside closure of f of E. So that shows f of x is in the closure of f of E. But we obviously have the other direction of the inequality. So here we have this equality. So that concludes part A. Okay. All right. Okay. So next, we want to show part B. Okay, so here's the proof. So first we define a function phi that goes from x to r. So what does phi do? So f of p is equal to the distance of fp and gp. So the output of phi p is the distance between f of p and gp in the space y. Okay, so first we want to show that phi p is continuous. All right, so how do we show this continuous? So we want to show the following. Dy f of p g of p minus dy f of q g of q. So note that this is absolute value of phi of p minus phi of q. Okay, so if we can show this is less than dy f of p f of q plus dy g of p and g of q, then we are done. Okay, so I claim that this inequality implies phi p is continuous. And why is that? Because think if p and q are very close, we know f is continuous, so f of p and f of q are very close, right? So this is small, and same thing with g is continuous, so the distance between gp and gq are also very close. So that is saying if the difference between p and q are small, then the difference between phi p and phi q are small, since they are bounded by a very small number. Okay? So now our task is to establish this inequality. So how do we do that? Note that this absolute value equals to either dy, so this is d, okay, so this either d f of p, g of p, minus dy f of q, g of q. Okay, so here I'm omitting the parentheses around p and q. So this is either equal to this or the other way around, right? dy fq minus gq minus dy, sorry, this is comma, dy f of p gp, right? So the absolute value is equal to one of these two things. Okay, then we will use this triangle inequality, then use the fact that dy fp gp, this is less than or equal to dy fp fq plus dy fq gq plus dy gq gp, dy gq gp. Okay, this is a triangle inequality, right? And then you plug this into both, then we'll see in both cases this inequality is true. Okay, so now we have proved that phi of p is continuous. All right, so what is the zero set of phi of p? So we know from the previous problem that the zero set, well, first let me write down the zero set of phi. So this is order p such that f of p is equal to g of p, right? This is by definition of f, and this is zero set. So we know that the zero set is closed, right, from the previous problem. So we know z of phi is closed. Okay? But we also know that this set contains a dense set, right? Because by assumption, E is in z of phi, right? And z of phi is closed, so that implies the closure of E is in closure of z of phi. But z of phi is closed, so you can get rid of the closure there. Now E is dense, so the closure of E is actually equal to x. So x is equal to z of phi. So in other words, for every p in x, f of p is equal to g of p. Okay, so next, a boundedness theorem. It's a theorem that we all very familiar, but let's now prove this rigorously. So let me first state the statement. Let I be a closed and bounded interval. Okay, closed and bounded. We have f that is continuous from I to R, and then f is bounded on I. So a continuous function on the closed and bounded interval is bounded. All right. Okay, so let's prove that. Suppose f is not bounded, then for any n in n, a natural number, we can find xn in I such that f of xn absolute value is greater than n, right? So for natural number 1, 2, 3, 4, 5, etc., we have the corresponding x1, x2, x3, x4, x5, right? With the absolute value of f of x1 is greater than 1, the absolute value of f of x2 is greater than 2, etc., etc. Now, these xi's, they're in the bounded interval I, right? So here we have a sequence, we have a bounded sequence, right? And we know that for any bounded sequence, we have a convergent subsequence. Okay, so that's the Bolzano-Weierstrass theorem. Every bounded sequence have a convergent subsequence. Okay, so we take a subsequence. So this is our sequence xn, right? Take subsequence, say xn sub r, convergent. Suppose it converges to x. Okay, so we claim that this x is in I, right? Because I is assumed to be closed. So the limit of the sequence should also be in this I. Okay, now f is continuous, so f is continuous on I, so in particular it is continuous at x, right? So we can consider the sequence f of x and sub r, right? This is also convergent, and that converges to f of x. Okay, that's by definition of continuity. Okay, and we know that a convergent sequence is bounded, right? Convergent sequence bounded. So that this whole thing, this whole sequence is bounded, right? But that's a contradiction because f of x and r should be greater than or equal to nr, right? Which in particular is greater than r. All right. So, but r is not bounded. R can be arbitrarily large, right? So on the one hand, we say it's bounded. On the other, it's not bounded. So it's a contradiction. So next, I'm going to illustrate that each of the assumption is needed, is necessary. So we cannot relax the statement any further. So first, the interval must be bounded. Okay, boundedness. So if the interval is unbounded, then f is not necessarily bounded. So a trivial example, say f of x is equal to x. Okay, if our interval is unbounded, say from 0 to infinity, then certainly f is not bounded. Okay, and second, the interval must be closed, because if the interval is not closed, consider this function g of x is equal to 1 of x on 1 to 0 to 1. Okay, this interval is bounded and not closed, but this function is continuous on this interval. But it should be obvious to you that this function is not bounded on this interval. And 3, the function must be continuous. Okay, because let define h of x is equal to, say, 1 of x if x is in 0 to 1, and is equal to 1 if x is equal to 0. Okay, then this function h of x is defined on the interval from 0 to 1 to r, right? But it's not continuous at 0. So as you can see, this even though this is closed and bounded, g of x is not bounded. So each of the three conditions are necessary. So here I should stress that f is continuous. Okay, we cannot relax the statement any further. Okay, so next I'm going to state, but not proving, some useful theorems about continuous function. So the first is the Max-Min theorem. It says that let I be a closed and bounded interval, and f from I to R is continuous, then f attains absolute maximum and minimum on I. Okay, I think this theorem is very very intuitive to you if from calculus, right? I'm pretty sure you've all seen this in calculus. So I'm not going to prove that. And next, the location of roots theorem. Okay, so let I be a interval and f be continuous if f of a is less than 0, less than f of b, or f of a is greater than 0, greater than f of b, then there exists a number c in AB such that f of c is equal to 0, right? So this is 0, okay? If at one end it's less than 0 and the other end it's greater than 0 and the function is continuous, then the graph has to pass somewhere between A and B, right? It may cross it more than once, but there has to be at least one crossing. All right, so it should be very intuitive, at least from the graph. Okay, so from here, a corollary of the theorem is the intermediate value theorem. Okay, intermediate value theorem. So says that's what says I is an interval. So f from I to R is continuous. So if A, B is in I and K satisfies, f of A less than k, then less than f of b, then there exists a c in I, c between a, b. Okay, depends on which one is bigger, such that f of c is in k. Okay, so it's very similar to the location of roots theorem. You just replace 0 by k. So the proof is one line. So the proof is that you consider the function h of x equals to k minus f of x. Okay, then you would have h of a less than 0 less than h of b, or h of a greater than 0 greater than h of b, and then you just apply the location of the root theorem. Okay, so a consequence of this intermediate value theorem is the following. So let me state as a corollary. So I is equal to the interval AB, closed and bounded, and f from I to R, closed and bounded. F from I to R is continuous, and K is any number that satisfies this. Then there exists a C in I such that f of c is equal to k. So this is a corollary of the intermediate value theorem and the max-min theorem, because we know that by the max-min theorem, infimum mode f of I is equal to, say, f of a for some a in I, and this is equal to f of b for some b in I, and then it just follows from the intermediate value theorem. Okay? So another consequence, so let I be closed and bounded, and f from I to R continuous, then the set f of I, the image of I under f, is also a closed and bounded interval. Okay, so how do we prove that? So let M be the infimum of f of I, and big M to be the supremum of f of I. Then we know that M and big M, they both belong to f of I, right? Because there exists an A such that f of A is equal to M, there exists a B such that f of B is equal to big M, and A and B are both in I. Okay, so we know that M and M both belong to f of I. Also, by definition of the two M's, fi is inside this closed interval, right? So if k is anything from this interval, then by the previous corollary, we know that there exists C in I such that f of c is in k. Okay, so anything there is in the image of f. Okay, so that implies k is inside f of I. Now, since k is arbitrary, this whole thing is inside f of I. Okay, so combine the two, we can see f of I is actually equal to this interval. All right, okay. All right. So, okay, so here is a warning. Um, so what we have shown is that f of I is equal to this interval. The lower bound of the interval is the infimum, the upper bound is the supremum. It is not true that, so say f maps AB to R, so it is not true that f of AB is equal to FA FB. Okay, so this is not true. So look at this example. Say, so this is A and this is B. Okay, so our F goes like this. So you decrease, then you increase. So the image of AB under F is this interval. Okay, whereas f of A and f of B is only this smaller interval. Okay, all right. So I'm gonna stop here, and if you have questions, please come by to my office hour. I'll see you next time.